Okay, now we're going to enter into the world of complex numbers. And a complex number is written in this form, a plus bi, where a represents a real number component and bi is the imaginary. And if b were equal to 0, well, let me say this first. A and b are both real numbers, would be both real numbers. However, if b was equal to 0, then we would just have we'd be just left with a real number, because 0 times I would be 0. And if a were equal to 0, then we would just be left with a pure imaginary number of bi. But here on page 248, we're being asked to evaluate complex numbers. This is example 4. And we're going to be looking at an equation that has both real components and imaginary in them. And so here we've got, let's see, and we got 5x plus 1 plus, in parentheses, 3 plus 2y times I, and that's being set equal to 2x minus 2 plus, in parentheses, y minus 6i. Now, in order to, and we're being asked to evaluate for both x and y. And so in order to do that, we are going to break this down into its real components and its imaginary components and break that apart and solve for each. So here I've got, this is my real component, and here's my second part of my real component, and then this is my imaginary components. And my real components have the x variables, and my imaginary components have the y variables. So in order to solve this, I'm going to do this. I'm going to say 5x plus 1 equals 2x minus 2, 2. And then over here with my imaginary components, I'm going to have 3 plus 2y equals y minus 6. And I'm just going to simply solve these two equations. So over here, I'm going to subtract the 1 from both sides, and I'm going to subtract the 1 from both sides, and I'm going to subtract the 2x from both sides. And when I do, I'm going to be left then with 5x minus 2x is 3x, and negative 2, negative 1 is negative 3. And I'm going to divide 3 to both sides, and so x is going to be equal to negative 1. Now over here in my imaginary, I'm going to do the same thing. I am going to subtract 3 from both sides, and I'm going to subtract y from both sides. So when I've got 2y minus y, well then I'm going to be just left with y. And negative 6 minus 3, because I'm subtracting 3 from both sides, is just going to give me negative 9. So we're saying that x is equal to negative 1, and y is equal to negative 9. Now, if I wanted to prove that and check myself, I could substitute by going back to the original equation and substitute in negative 1 for x and negative 9 for y, and we'll see if these two statements equal each other. And I think I've got enough room to do this. We're going to try it. So I've got 5x. Oh, no, not 5x. I'm going to substitute in negative 1. 5 times negative 1 plus 1 equals, no, excuse me, not equals, plus, getting ahead of myself, plus 3 plus 2 times negative 9, and all that's being multiplied by I, and that's equal to 2 times negative 1 minus 2 plus negative 9, negative 6 times I. Barely squeezed it in. All right, so let's just solve. So 5 times negative 1, well, that's negative 5 plus 1 plus So let's see, I got 3 plus 2 times negative 9 is going to give me negative 18 multiplied by I equals, well, 2 times negative 1 is negative 2, negative 2, negative 2, plus, and then negative 9, that is a negative right there, negative 9, negative 6 is negative 15I. Let's continue to solve. Well, then negative 5 plus 1 is negative 4. 3 minus 18 is negative 15. And then I distribute the I, so that's minus 4 minus 15I here on the left side. And let's see, negative 2, well, that's negative 4 also. And minus 15 times I is going to give me negative 15I. And so we have proved that in this original equation up here, if when x is negative 1 and y is negative 9, this equation is in fact true. We have evaluated a complex number. Now, next up, we're going to look at adding and subtracting complex numbers, multiplying complex numbers, and then dividing complex numbers. And when we look to divide complex numbers, we're going to be introducing something called the complex conjugate. Can't wait, right? I know.